thank the organizers for putting this together. I have combined 2 talks into one, so hold on to your seats. But it was just too tempting to not, with all these metrologists here, to not show results from these 2 experiments. So I want to thank my collaborators, especially Andrew Jordan, whose work I've really enjoyed working with. I moved recently to Chapman University about a year ago, and I worked with Andrew a lot when we were both at University of Rochester, but now we're both at Chapman University. Thank my students, Oni, Derek, and then Abhishek, who works with Andrew, and then some collaborators, Barbara Soda, Akim Kempf, and then some students and professors at the Hebrew University with the gyroscopes, and Stefania and Umberto, who are collaborators on the liquid crystal. So I'm going to try and do this efficiently and hopefully helpfully. So first, let's talk about the standard quantum limit for phase estimation. Everybody here knows what the standard quantum limit for phase estimation is, I assume. But there's a very simple way of thinking about this in the quadrature space. We know that the electric field for a coherent state has an uncertainty of 1/2. We know that the distance away from the origin basically is the amplitude square root of n. And so if you just take the subtended angle, delta theta, and do this simple relation, you can arrive at a very ad hoc approach to how you get the phase estimation standard quantum limit. Now, people have been working on this very hard to go beyond the standard quantum limit phase estimation. A lot of them have been working, for example, with quantum techniques. A famous one is Howell and Burnett that used entangled photons to do this. These Howell and Burnett states were generalized by John Dowling's group to look at, for example, improving the resolution in interferometry. The problem is it's very difficult to do this, and the problem is that typically to get the results you need to post-select. So if you actually look at all the resources coming in and don't post-select, a group, Masewu Nam, Jeff Pride, basically showed that if you don't do any post-selection, here's your standard quantum limit. You can beat it without requiring post-selection, but it's really hard. So in the few photon limit, it's really hard to beat the standard quantum limit. It's also hard to beat the standard quantum limit in the many photon limit. And when I mean hard, I mean, for example, getting a few dB of squeezing. For example, at LIGO, they got 3 dB of squeezing using squeeze light in their system. So at the high photon regime, it's difficult. In the low photon regime, it's difficult. But it's doable, just hard. So now I want to talk a little bit about some of the things that we've done. So a few years ago, about 10 years ago, Stefania, Umberto, and I basically took a liquid crystal, which is if you take 2 laser beams going in, what this liquid crystal does is there's a conductive material that basically takes the interference pattern between these 2 laser beams and writes that into a grating from which the 2 beams can scatter into various modes. And if you look at what happens in those various modes, there are phase, there are gain, there are many things happening here. What we did is we said, well, let's just look at this I0 and I pump. And we'll put, for example, a laser beam going into this PZT, hitting off of this mirror, which is causing a Doppler shift, and then basically this pump, which has no shift. And what we could see is that we could measure down to microhertz per root hertz sensitivity in shifts. So about 1 part in 10 to the 20 in frequency shift. Now the reason why this is possible is because what we had is a gain curve, which means that if I put 1 laser into the crystal, another laser into the crystal, and I change the relative frequency of those two lasers, then I can put all of my power into one and pull it out, or vice versa. And that's what I mean by this gain curve. So if I take the balanced detection, balanced power between those two, I can get a very steep gain curve, which means that I can turn basically frequency into amplitude. and we can get this basically what is the shot noise limit for our particular device. So in our particular case, chi was about 1 second in terms of its slope. These are basically what the Kramers-Kronig relations look like for gain and also for phase between all the various modes. And we're working on this particular gain peak right here, which also means in the Kramers-Kronig region, centered around that, it's phase insensitive. So the relative phase between them, it becomes insensitive to those two objects. Now for frequency versus phase, so basically for what I already said, phase estimation goes as 1 over 2 root n. Now we have a liquid crystal light valve, 1 over chi root n, and then, but generally speaking, the Hellstrom bound is root 3 over 2 pi root n. And so, but there are situations in which I'm going to show you that this liquid crystal light valve can be really, really valuable. Okay, so now let's think about a Sagnac interferometer. In a Sagnac interferometer, the basic idea, how people mostly think about that is as your Sagnac rotates, it takes longer to go for the light to go around back to where it came in versus the other path. And so what you think about is you get some sort of relative phase between those two, and then you can use standard quantum limited phase estimation and be able to estimate the rotation rate of this device. So this is what I would refer to as the beam splitter is both the source and the receiver, if you want to think about it this way. It's a closed system in that the beams end up going back onto themselves at the output. So now I'm going to talk about this from a Doppler point of view. So I just want to remind you of an important equation. Most of us are used to thinking of the Doppler shift as 2v over lambda times cosine beta, where beta is the incident angle relative to a moving mirror. But if the moving mirror is not moving in the direction of the optic axis, then you get another angle here, alpha. And so this is the what we would refer to as the Doppler shift from an arbitrarily moving mirror. Okay. People have been arguing for about 85 years whether there is really a Doppler shift inside of a Sagnac. And this, for example, in this paper by Malikan, he says there are 2 reasons why Doppler shifts should not exist inside of a Sagnac interferometer. One is that the emitter and the receiver, the beam splitter, are basically form a closed loop. So, for example, in this system, what you have is a beam splitter that's moving, that's rotating. As the light comes and hits off of it, then what we're assuming is it's going to be blue shifted, and it's going to be blue shifted going around here. But when it comes back to this beam splitter, it's going to be exactly red shifted in the opposite amount. And so the blue shift is canceled by the red shift, but in this direction, there is no shift because it isn't shifted by the beam splitter. Here it's moving transversely. That's like saying if I take a mirror like this and I shine a light coming off of it, there's no Doppler shift, right? If it's moving transverse. And so there would be no shift here, no shift here, no shift here, assuming that the rotation is about this center. So basically in this particular case, the emitter is the beam splitter, the receiver is the beam splitter, and so they're co-moving. And also in a material medium of index n, Doppler predicts 2n squared fold larger signal. So we broke the symmetry and said rather than consider the light beams to go back onto themselves, let's consider a displaced Sagnac interferometer where we change the tilts of these mirrors so that we can get an angle that comes out. If that's the case, then what we can do is we can essentially leak out a small amount of Doppler information. And so we can find that this delta F predicted based upon if there are Doppler shifts, this is what we would expect. And it's in actually excellent agreement with what we observe. And instead of being, so this is a distance L here, omega is the rotation angle, epsilon here is basically this opening angle that we use for the liquid crystal light valve over 2 lambda, which is orders of magnitude more sensitive than using other techniques. So I'll show you here in a moment. So basically what we have is we have a platform. Everything is all on one rotating platform. I have a fiber laser coming in. It goes into this Mach-Zehnder interferometer. Here's our axis of rotation. We can move this is a little plate, this is a little plate. We can move these relative to each other. We can slide these relative to each other, so we can increase the size of the interferometer. We can also shift the interferometer relative to the axis of rotation. We pass it through a liquid crystal light valve and then put it onto a bounce detector. And this is all in a single frame. We're then taking a piezoelectric device, which is essentially causing very, very small rotations. And what we are basically showing here is we wanted to prove that this could not be a phase effect that we're measuring, because if we put a phase offset into this liquid crystal light valve, think about this original experiment, then what we see, this is a square wave we're putting in. What we see is that it returns back with no offset. So we initially make the change. We know that a change in phase corresponds to a frequency shift, but then it goes asymptotically back to the origin and just keeps returning to the origin. So no offset actually occurs in here. But if we then put in a triangle wave, in other words, this is moving with constant speed back and forth, then what we would expect is a square wave. And that's what we see. Of course, it takes a little bit of time to come back into equilibrium because these liquid crystals are slow devices. And indeed, we get a square wave as predicted. So how well can it do? Well, this is, if I were to take a Sagnac interferometer with exactly the same power, with exactly the same size, take every parameter associated with a Sagnac interferometer, use phase estimation, and this would be the shot noise limit of the standard Sagnac. What we did is we put a 2.2 microradian signal, microradian rotation on this platform, and then at this particular frequency, and the amplitude spectral density shows that we are orders of magnitude below the shot noise limit for phase estimation. So meaning that our frequency estimation technique is orders of magnitudes better. And the shot noise limit of our phase estimation, of our frequency estimation, is actually several orders of magnitude below this yet. So even though we beat the shot noise limit for phase estimation, our frequency estimation technique can do much, much better than this is actually showing. Now, some interesting results are that what we found out is that this whole device increases its sensitivity as we move it away from the origin. We also found that it is indeed linear with the length of basically the circumference rather than the area of the device. Here's what the area would predict. Here's what a length increase would predict. And then these are just sanity checks showing that it's linearly proportional to the piezo amplitude and the piezo frequency, as we would expect for an interferometer. Now, why this works and why is it so sensitive? So basically what you can think about is if I have just some green laser coming that then gets split into two, for example, this is a beam splitter interaction that then takes one beam and frequency upshifts it and takes another beam and frequency downshifts it. After a given amount of time, these, so they're created in phase, and as those beams propagate in time, then they go out of phase simply because this is going to oscillate more quickly. But it only works up to the, so basically these are created in phase. These are always going to be the same amount of phase differential after a given amount of propagation time. And why is that important? Because in phase estimation, if I were to use phase estimation for doing frequency estimation, then I would get my change in my phase integrated over my time. But here, the propagation time is simply C over L, which is, sorry, my propagation time is, L over C. I meant, oh yeah, okay, yeah. I'm sorry, I put this in backwards. So my propagation time is actually L over C. So it's an incredibly short amount of time. Wait a second. Yeah, so this should be df dt, and then this should be
it's in a couple division signs.
Yeah. Okay. Yeah. So that's so basically what I'm going to see is that the sensitivity is incredibly low for this phase estimation technique. Sorry, I just did this right before I started the thing. I should have been a little more careful. But this is actually very, very, very sensitive. Okay, so that was a very fast thing, and I understand, but I wanted to get into both. So super radar, this is something that Andrew and I have been working on, along with our collaborators, Barbara Soda, Akim Kempf, and some of our students. So we're all familiar with time of flight radar ranging. Basically what you have is you have some sort of input pulse that comes off, hits off of a target, goes back, and you simply take a time of flight, and you say, well, how far away is that target? Now, how is radar used? Radar, for example, is used in ground penetrating radar, archaeology, sedimentology, utilities, treasure hunting, law enforcement, grave detection, navigation, traffic control, shipping, automobile, planes. It's used extensively commercially. It's used, for example, in weather. For example, here's a tornado signature with tornadic debris. It's used, radars can tell the difference between rain, snow, sleet, all different kinds of things. It's used in tracking locusts, in light pollution, aviation, looking at biodiversity. It's even used, for example, in medicine, where here is an EKG sensor and here is a radar signature. So it's used extensively. One of the things we're interested in is seeing if we could actually use it even in imaging, biological imaging, if we can get the resolution high enough. So now, what is range resolution? And this is very different than range accuracy. So when we talk about range accuracy, we're asking how well can I know the distance of a target? And now what we're going to say is how well can I know the distance between two targets? And that is a really, really important question because it defines how things are characterized. So for example, in range resolution, if I have two objects, then if they're separated by sufficient value, then I'm going to get these two return pulses. However, radar is coherent, so these waves sum, and so you see that you get these two pulses that are measured. But if I have a single pulse, and then the pulse is much fatter, then it hits off these two targets, then what you see is that you get another pulse, but it's broader. And it can be hard to determine what is the resolution there. So why should we care? Shorter pulses equals higher resolution. Short pulses have high frequencies that are absorbed more strongly. So that's a really important thing. And for example, here's a commercial, people are just selling these ground penetrating radars. You can get very, very deep penetration, for example, with 100 megahertz. People can get down to 40 meters underground, but their resolution is of the order of meters. At 6 gigahertz, for example, you can get centimeter resolution, but with centimeter penetration depths. And so it's really, really important. Frequency is, the lower the frequency, the better the penetration, but also the worse the resolution. And the big reason is, one of the big reasons is water. And water has this, flat region between 1 megahertz and about 100 megahertz. And then it just shoots up after about 100 megahertz really dramatically. There are also many other reasons why, but almost in every system, the lower the frequency, the better the penetration. So others have tried to overcome this range resolution limitation. And basically, what is the limitation? It goes as the inverse bandwidth. As you saw with the pulse, the shorter the pulse, the better the resolution. But more generally speaking, people think about it in terms of the inverse bandwidth of the pulse. So what have we done? So rather than considering interference to be a negative thing, we think of interference as being a positive thing. We also think of, rather than resolving in time, we think about resolving in amplitude. Can we resolve objects based upon amplitude? So what we're doing is we're going to compare three pulses. One, this is just a standard sinc squared pulse, and it represents what we're going to refer to as the Rayleigh bound, because it looks an awful lot like a one-dimensional version of an airy disk. Okay, so this is the Rayleigh. What basically in an airy disk for spatial resolution, people say if I have two objects that are separated by a distance equal to or greater than the distance between the peak and the first minimum, is considered resolved. And so this represents our standard. And we're in these units, we're going to consider a unit of 1 or above to be resolved. Then what we did is we used a band-limited function theory to write out this other pulse. And this other pulse has regions of flat and regions of steep components, and then we're doing a triangle. I'm going to show you on the triangle, but we've stopped working with the triangle wave. We're just using band limited, but it's a nice way to demonstrate things. So notice, so we call these self-referential interference functions, and that'll be understand why in a minute. You have regions of steep slope, then you have regions of no slope, zero gradient or steep gradient. And then what we're going to basically do is we're going to take these functions and pass them off of, in a three-dimensional space, we'll hit them off of objects where they, for example, have two different depths. Those those waveforms will interfere and make a composite pulse that then gets sent back to a receiver. And there's a very simple way of doing this simply with cables by, for example, using the impedance mismatch that you get from having a cable exposed to air, for example. And so you're going to take one pulse that's going to just pass right through, and another pulse that's going to go down here and interfere with that, and you're going to get these composite pulses as is shown. So here's the idea. So I take this composite pulse, I hit it off of the target, and we see what happens. So when I add these two coherent signals, I add them together, what I see is I'm going to get, this region is still going to be flat. There are going to be curved edges, but the height of this is still going to be the same. The sum of these is going to give me something that is not changing in terms of its height, but these two intermediate peaks do get change their height. And so we can define a single parameter estimation, which basically says I'm going to take the differential between the height of these peaks relative to the height of these peaks. And this is very much in the light of what we used to do for differential or precision transverse beam deflections. What you do is you have a split detector, you put all of your light on the split detector, and if it moves to one side, more power goes to one side of the split detector and is reduced on one. And so it's like looking at a fast changing signal in terms of its difference divided by a slow changing, which is the sum of the beam detectors and of the power on the detectors, and that gave a parameter estimation. And so this is our parameter, and we were basically able to show that we could get very, very sensitive changes here. This is about a range resolution 100 times better than the standard range resolution that people are used to. We wanted to use band limit as function, so like a radio, you're only using a small set of frequencies. We have to constrain our functions to be within a frequency band. And when we use these band limited functions, remember one is when it would be completely resolved temporally. Now what we're doing is resolving spatially, or resolving in amplitude. And this, for example, this would be 0.0 would be when there's no separation out to, for example, 0.1. So we can get resolution on the order of about 0.05, even with a band-limited function. Now, if I blow up this region where it's nice and linear, where the function has become linear, and then I look at very, very small changes in relative position, I can know the separation here. I can know 35,000 times smaller than the range resolution. So I can know the accuracy of the distance between these two objects for sub-resolved objects 35,000 times smaller than the range resolution that people normally consider as the bound. So now, so let me just conclude here. Wow. Okay. Even with time left over. So we're using maximum likelihood techniques. Andrew's really been spearheading this. He's looked at fundamental bounds using the Fisher information and saying how well can we know single and multi-parameter estimation of these pulses. This just went on to the archive. We want to be able to use this multi-parameter estimation, for example, to reproduce a scattering distribution. So we want to know how many scatterers, we want to know what the whole distribution looks like. And so we want to see deep insides, deep sub-wavelength imaging. And we believe this can have a lot of practical purposes in many fields. We want to apply this in free space. And for example, we also used an optical frequency comb. And with this optical frequency comb, we showed that using the spectral techniques and our own parameter that we could use, we could actually measure 500 nanometer distance resolution, even using waves that are 5 meters in length. And in the actual optical domain, we predicted yoctosecond relative time uncertainty between two different objects in the distance. So we believe this can lead to extremely high sensitivity to knowing how far apart two objects are at even very great distances. Okay, thank you.
All right, we have plenty of time for questions.
Hi, nice talk. When you do maximum likelihood estimation, that's for a given initial pulse, right? The one that you drew before.
Yeah, so...
And how do you know that's the best one?
We don't necessarily know it's the best one.
Okay.
Andrew's actually been working on optimal pulses that we can put in, basically using the differential between the eigenvalues. He basically came up with so there's a very trivial result, which is the best one should be the biggest eigenstate and the lowest eigenstate in your system, which would be the two band edges. Well, that would just be a cosine wave and an offset. But that's trivial and it doesn't actually work. And so the next non-trivial thing was to add a low frequency and a high frequency component, and that's something that we need to, we're still exploring. Andrew, do you want to add some more onto that one?
Yeah, not to steal too much of your time, but indeed, so what you could find is you say if you have this problem of coherent summation of pulses and you're trying to estimate the distance, one can calculate the Fisher information. And one of the things I wanted to stress in John's talk is that in the remote sensing case, it's very, very different than interferometry. It's very different than the optical case in the sense you only take a very, very tiny fraction of the light back you send out. So you have to account for the fact that you have a huge amount of loss and to take that into account in your estimation problem. And when you find this quantum Fisher information, it turns out if you have equally weighted reflectors, then the information involves, actually, it turns out in the deep subwavelength case, it turns out to involve something like the variance of the momentum squared in the shape of the pulse you send out. And so we have results on this efficient information, and we also have some new results on what this optimal pulse is. So I can tell you more. I can actually draw you some cool pictures after the talk, too.
Thank you for a nice talk. I have one question and one comment. So the question is that it looks like you are still using the high frequency component of your composite pulse to sense, to get the high spatial resolution, right? You have this sharp part of your pulse, right? And it's, as I understand, it's really those sharp part that gives you useful information.
Okay, so you're asking about this one right here.
Right.
Okay, so this is not a band-limited function because you know that in order to create a triangle pulse, you need an infinite series of frequencies in order to be able to reconstruct that. Mm-hmm. So we aren't using these.
So this is just for explaining.
We wanted to make a proof of principle demonstration. So if you actually, so there's a general theory that says if you look in the spectrum and you do 3 dB down in the spectrum and you define that as your bandwidth of your pulse, then you can say that's the best resolution that you can get. So, but what we're saying in here is, well, that's not necessarily true. If I look at the 3 dB down of this particular pulse, or the one that you're seeing up here, and you then define that as your bandwidth, we can do much better than that. However, for all practical purposes, we don't want to require infinite spectrum. So what we're going to do is only use band-limited pulses, which is this result right here, and based on this function right here, this orange pulse, which is band-limited, meaning it has a lower band, a lower bound and an upper bound on frequencies, and there's nothing beyond. There's no higher frequencies beyond those values.
But it's still the higher frequency component that's more useful.
Yeah, so in here, the higher frequency components here are the reason why this is so dynamic. Because, sorry, if I take this function and shift it relative to itself, the regions where the high dynamic elements occur are all in here, whereas there's much less dynamic in these side lobes. And so you want as much bandwidth as you can. Here you want as much curvature as you can in the middle and very little curvature on the sides.
Right, but still, if you consider the penetration depths of your composite pulse, it will still suffer a similar problem as traditional.
No, because in traditional, so what you can think about is let's think about this graph for a moment. Imagine that you've created a band-limited pulse that is between, say, 10 megahertz and 80 megahertz. There are no frequencies beyond 80 megahertz. Like a triangle, we would have frequencies beyond 80 megahertz. And so the whole bandwidth is on a flat region of the transmission through the medium.
Okay, yeah, I think this is very much like a weak value. your weak value method. You're preparing a very special state, which has certain distributions of frequency components. That's your state to start with, and then when you detect certain features of your pulse, meaning those fatter flatter region, the amplitude of those, and that's like a post-selection. So I think the essence of your method is somehow like this big value problem that we worked on before.
Yeah, so there is some very close similarities. I designed these functions to use so that I could make a parameter that was like this, just because I knew it worked so well in so many other regimes. So that I purposely designed functions that gave me this behavior, which is just standard beam deflection.
Right. So it's a very clever
parameter estimation.
redistribution of resources, I think.
Yeah, I don't know if this will necessarily be the optimal in the end. In fact, I don't think it will be, but it's more like just the initiation of beginning to think about this. I think some of the other things that we're thinking about right now in terms of decomposition, some things that we've discussed with Menke while we've been here, that we can actually reconstruct distributions based upon orthogonal functions, and that the orthogonal functions that we would send to the system would allow us to pull out all of the scene information. So anyway, think of this as just the preliminary as opposed to the, so is it cool? I think so. But I think of it as a very preliminary method.
Yeah, just a short comment. I think that you just said this is a preliminary. Indeed, there might be a lot of space to improve. For example, right now, I don't know what exactly you are looking at your detector, but I imagine that if you look at multiple degrees of freedom in your pulse, you may be able to extract a lot more information. For example, not only the amplitude, but also the phases, the correlations even between different detectors and so on. So, because this is all about information extraction.
Yes, I agree. And in fact, we think the best thing to do is send in an orthogonal set of functions to determine the coefficients and then reconstruct using that. So we think that's, yeah, thank you.
Thank you for the talk. I have a question about the gyroscope. So you are using this light valve object to measure the frequency difference between the beams. And it's on me. I don't know how to think about, in quantum mechanics, a light valve sort of detector. So instead, I'm going to do what I do understand. I'm going to ask, could I replace the light valve detector with two heterodyne detectors and measure the beat note between them? I generate two independent beat notes, and I would ask, what's the frequency difference between those beat notes?
Yeah.
Or do you find that you lose the Doppler shift once you account for like the mirrors you have to bounce off of?
So that's what I was trying to emphasize on this.
Yeah.
So what happens is, what I'm doing, if you want to think about, if there really is a Doppler shift that's happening, then what I have is I'm taking a beam coming in. When it interacts with the beam splitter, I can think about it splitting up into a blue and a red component. The blue has a faster oscillation. The red has a slower oscillation. And the longer they propagate, the more out of phase they become. When they get back to the beam splitter, they will have acquired a differential phase between them. And that differential phase, the longer I have to propagate, the more that will go out of phase. So, but then if I perform a phase measurement on them, I get a phase differential measurement that I perform on those, and then it becomes a phase estimation task. So then what you're going to be doing, so really in this particular case, it's the propagation time that matters, not necessarily the integration time of your detector. The integration of your time of your detector will improve the number of measurements you get for phase estimation.
Yes, but I'm going to consider the case where you have the epsilon angle opening.
Yes.
So in fact, you should have the Doppler shift appearing on each of those. So very naively, ignoring that the way you set up your heterodyne may have some canceling Doppler shifts that are introduced, and it may. But nevertheless, let me naively say, well, if I just actually take each of those beams and independently heterodyne them against the same common laser, I'll generate 2 beat notes. Let's say I put an AOM in, so I shift it up to 80 megahertz. One will be at 80 megahertz, and one will be at 80.1 megahertz. And that should be the Doppler shift, right? And so basically I look at the frequency difference between those, and I estimate how well I can do that. And I can use standard ways of thinking about how vacuum noise limits my ability to estimate a frequency difference. And is there some magic in the light valve? I just don't understand what the light valve is.
Yeah. So it's an excellent question.
Yeah.
And the reason why it's such a good question is because of this, the Hellstrom bound. If you can just integrate indefinitely, and this goes as T, and you get the number of photons here, but that's just going to be integrated as well, which is going to give you a rate times T to the 1/2. And so you're going to get T to the 3/2.
Exactly. And I think I could see that from doing heterodyne beat notes as well.
Yes. I'm just not sure I'm going to see that. I would really love to, because then if that is the case, I should be able to get, after a day's worth of measurement, 10 to the minus 19 a rotational measurement in the rotational. Is
the issue that I basically also have to introduce an opening angle epsilon in my 2 heterodyne reference beams?
Yes.
And essentially, somehow, that's going to end up giving exactly the canceling sort of Doppler shifts on the heterodyne references, which means you won't see it in the beat note, which means there is something magical about the light valve. Yeah, I don't understand, like, what's the magical property? And maybe I'm wrong. Maybe, in fact, you can see it in beat notes. But I feel like it's a really critical question to ask.
Yes.
For, like, digging into the physics.
And it is a really gnawing question for me.
Okay. Anyways, that's the thing that I was sitting here going, this is the thing I want to understand.
Well, I'm glad you have that gnawing feeling, because it has driven me
because in the
crazy
end, everything is simple. We should be able to understand things in terms of simple physics.
The thing that's really interesting about the light valve is it's phase agnostic. It doesn't care, because of that steep dispersion. If you think about that in terms of amplitude.
You can apply a step function to the phase, and at longer times after the step function.
That's right. Yeah. And basically, you can think about it from the Kramer's-Kronig relations. It's in that region of steep gain, there's essentially a flat phase, which means it doesn't really care what the phase differential doesn't really matter. Yeah. So the interesting thing about that is it doesn't, when I'm doing this experiment, let's see, where's my, when I'm doing this, it doesn't care that they were created in phase. The liquid crystal light valve, it doesn't care.
I understand, yeah.
All that matters is that this is blue and that this is red.
Yeah.
And that's the interesting part. Now, it doesn't like if you suddenly give a phase shift to this, because that shows up as a frequency shift, but it doesn't care if this is red and this is blue, or what the phase offset is here. So I'm glad it gnaws at you, because it's gnawed at me, and I really want to get down to the bottom of this. Okay.
So you had 2 topics, so I get to ask 2 questions.
Okay. That's fair.
The first question is sort of related to Jim's question, but I learned that Sagnac effect, the rotation phase shift is proportional to the area, and if it's Doppler shift, then it's not. And so it seems that in your experiment, I can rearrange the optics to make the area goes away. And just by returning the light back reflected, but not through the beam splitter. So the areas goes away. In principle, if it's a Sagnac effect, then you shouldn't see any phase shift. But the fact that you do, and even you mentioned that you change the distance as an area, it seems to have less effect than you change the distance from the axis of rotation. I forgot exactly what it was phrased, but can you explain that? What are you really seeing the Sagnac effect, that is?
So what we see is that it is linear in the length, and that it's not a function of area.
Yeah.
So it does seem to be a function of Doppler shift. And what I think is really happening is a general relativistic effect in which we're actually, because we don't see the rotation of the Earth. And so what I think what's actually happening, and I'd really love a general relativist to jump in and say, oh, that's what's happening, but is you're looking at a Doppler shift in one, instantaneously you're creating a Doppler shift on two beams, and then you're going to a different part of the rotating frame, which has would look like a different inertial reference frame, instantaneous different inertial reference frame. And so I think that's what ends up mattering, is that we are going from a place where it's moving quickly to a place where it's not moving quickly. And so the Earth's, that we would expect to see the Earth cause a shift, but actually it doesn't. And that's because it basically looks like simply just transverse motion of this whole device. If we're,
Okay.
so.
Probably warrant more discussion afterwards.
Yeah, maybe you can ask me afterwards.
Yeah,
we
yeah.
need
So
to get to
if
Mankay's.
Maybe. Okay, I'll ask the rest of the questions.
Maybe after. Okay. Yeah, sorry to cut it short, but we're.
Okay.